BC Calculus, Lesson 8.1, Integral as Net Change. So you've done all this before. Velocity of a particle moving along a horizontal line is given as ds dt equals the velocity, which is t squared minus 8 over t plus 1 squared. So if you graph this, you will get something like this, where this is, change the color a little bit, where this is t equals 1.25 seconds. And by looking at the graph of the velocity, we understand that it goes negative, meaning that particles moving left from 0 until but not including 1.25. And then we see the area under this is positive, so it's moving right from 1.25 not included to including 5, because that's our domain. And it's standing still at t equals 1.25. So that's what we call describing the motion of the particle. Now we have two major concepts to keep straight. This graph shows displacement. And it's basically just the areas. Got area 1 and you got area 2. So displacement says how far has it traveled from wherever it started. Position is displacement plus that, because that's our initial position. So if we did the integral and left the c value in there, which we don't need to do, I mean, we know what it's going to be, we would get, I'm not even going to write it out, I'm going to be very lazy, t to the third over 3 plus 8 over t plus 1 plus 9, because our original position is 9. And then we could put in t equals 1, and we'd get, this is s of t, by the way, we'd get negative 11 thirds. We put t equals 5 in, and we'd get 35. And that's just the position it's at. Now, pardon me, that's the displacement, it's gone. If I said, what's the original position? Pardon me, if the original position is 9, what's its position now? At t equal 1, the position is 9 plus negative 11 thirds, which equals 16 thirds. Yeah. And the position at t equals 5 is 9 plus 35, which is 44. Meters, centimeters, I think it actually says up here. I've kind of ignored that. Centimeters. So really should be more. Careful about that, because units is one of the things that gets missed the most in this lesson. And the other way to solve this is just by, if you're looking for position, say it's from 0 to 1 of your original function, which is t squared minus 8 over t plus 1 squared dt plus 9. And I'll just use that as an example of how we'd get 16 thirds. So we hit math, 9, go from 0, actually I'll go to 5. No, I'll go to 1. I said I was going to go 1, I'll go to 1. And we get t squared, we're using our dummy variable x here, minus 8 over x plus 1 squared with respect to that dummy variable, and while we're at it, plus 9, we should get 16 thirds. Math, enter, enter, and look at that, 16 thirds. So that's how we could do it with n int on the calculator. This also equals 16/3 centimeters. Now the only other thing we have to show is how do we find the total distance traveled, because it was going left and then it came back and went right. Well, the total distance is the absolute value. Not with a +9, because the distance is just where it's traveling, not its position. It's absolute value of displacement. And if we blast that out on our calculator, which I'm not going to do, I showed you the calculator once. Last time I tried this, it blew up my calculator. We would get 42.59, which is greater than the 35 displacement we had. So you can see it traveled and traveled, and this is a net displacement. This is a total distance traveled. Practice on that one. Takes some getting used to. We also know that acceleration can be integrated up. So if the acceleration is 2.4t, the velocity is the integral of 2.4t dt, and we're told that the original velocity is 5. So integral of 1.2 t squared plus 5. We want to know what the velocity is when t equals 8 seconds. We have 8 equals 76.8 miles per hour. If you're doing our Math Excel homework with this, watch out for your units. They get real confusing on the Math Excel. They do not get that confusing here. Okay, so how far did the car travel during those 8 seconds? Well, we'd have to do an integral again, but I'm not going to go and do all the messy work. You may or may not notice alternating between when I have to do some real integration and when I can just be lazy and let the calculator do it. Notice I didn't put the +5 in. Perhaps I should, but I don't think. Oh, I did put the +5 in. Boy, I'm talking out of my hat. Yeah, you need that because otherwise it's not going as fast. So let's see what we get. Integral 0 to 8. And see what I had up there. Squared. 1.2 squared plus 5 with respect to x. And this is actually where those units get a little bit crazy again. We get 244.8. This is what I was referring to in the Math Excel. I forgot that I actually did this. 244.8 miles per hour times seconds, because 0 to 8 is seconds. So it should just say miles, except we got to do some canceling. So we have to times 1 hour is 3,600 seconds. Seconds cancel, hours cancel, and we're left with miles. So once we do that, we find out it went 0.068 miles. It's pretty cool math. The remainder of this lesson talks about how integrals are net change. And you can calculate anything. If I know the rate of what's going on, rate of potato consumption here, then just keep an eye on what you're doing, and you can say the number of potatoes would be from beginning of 72 to the end of 73. That's 2 years. And just do the integral 2.2 plus 1.1 t dt. Just blast it into the calculator and see where it goes. And doing the math off to the side here, we get 7.066 million bushels. That's quite a bit. That's a million, by the way. Bushels. Quite a bit of potatoes. But yeah, that's how you do it. Turns a rate into the actual number on top of the rate. A pump, doing all this nonsense. How many gallons are pumped? Because it gives us gallons per minute. We have time every minute. Well, here we're just right back to Mr. Trapezoid Rule. Our gaps are 5, and the gallons equals 1/2 for the Trapezoid Rule, 5 for our gap, 58 plus 2 times all these in the middle, 60 plus 65 plus ... How far are we going here? Good, that's about what I thought. Dot 60 plus 60 plus 63. I don't recommend this, by the way. I screwed this up earlier today where I forgot to close parentheses and say there's 2 here. No, there's not 2 here. And it gives you the final number of gallons. Am I good on this? Gallons per minute, 5. Yeah, I'm good on this. 3,582.5 gallons. And so that's all the integral is, what's going on. If we needed the average time, we'd divide by 60. All that sort of stuff. So, one last example. How do we calculate work? Well, let's back up. We're using a spring just because we feel like using a spring. And when we apply a force to something, we're doing work. Lift a box up, we're working against gravity. Pull a spring out or in, we're working against the spring. So this is the formula for force in a spring. K is some constant. X is how far you pull the spring, so the distance. Meters, centimeters, watch your units. And forces in newtons. Could be other things, but that's the big one we're going to use. It's nice too. So the work is the integral of the work of the force, really. F of x with respect to x. So let's put one of them together. Takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. 10 equals k times 2. K equals 10 newtons per meter. So we got this initial condition, very similar to the last unit where we have to go find our k value. How much work is done in stretching the spring 4 meters from its natural length? Well, it's the integral of, from 0 to 4, of 10x dx, which is hopefully not that bad. 5x squared, 0 to 4, which is 5 times 16, which is 80. And x is given in meters, so then newtons is all that's left over. Pardon me. My bad. Work is measured in Newton meters, which I believe is known as a joule, but I'm not going to mess with that right now. Newton dot meters. Make sure I did that right. Nope, I did not. Because I screwed up over here. I got my k value wrong. K is 5. This is 5. This is 5 over 2. And this is 40. I think. 16, yeah, 40. Gotta be careful with my math. So anyway, that's how we would calculate work. We're going to come back to this. As you can see, it's a very, very brief introduction, but just wanted to hit you with it so you know what's coming. That's about it. Happy mathing.